Hello students, we are going to start a new chapter today, chapter number 5, which is about transient and steady state response. Okay, so the topic is not new for you because you understand what is the meaning of transient. We had a transient response for a spring mass damper system and a steady state also, right? A steady state, basically there are two parts, right? So one is what we call it a homogeneous solution, and the other is steady state we call particular integral, right? Particular integral. So this is the same thing actually, it's not different. So since we have already studied those, we will go very fast. Okay, so we'll just revise and we'll go very fast. You understand those terms such as critically damped, underdamped, damped, this kind of thing, like overdamped, those kind of systems which apply to second order differential equations, right? Second order system. Yeah. Earlier we had studied a spring mass damper system, right? So we had like this, right? So this is a KCM, and then we have mx double dot plus cx dot plus kx equal to f, and f could be of any type, right? So f could be sinusoidal, could be a just unit impulse, could be like a step input, or could be a ramp input like this. Yeah. What you see here is second order system or second order differential equation, right? What we did not study earlier is the first order differential equation, the first order system. Means we know few things about this one, but for first order system we do not know. So this I am going to describe a bit. Yeah, and but very easy. So we will find the solution very easily, and we will try to relate back to a spring mass damper system. What in terms of this, what is this first order system? Let's study this system. We have a spring here and just a damper here. That's it, nothing else, no mass. So K, C here, right? Okay. There is no mass. So equation, the original equation was, remember, mx double dot plus cx dot plus, we are applying a force here, plus kx equal to 0. When mass is equal to 0, our equation is ckx equal to 0. We get simply like this. Yeah. So if you see this order of the differential equation is 1, you call it first order system. Now, what is the response that we have to study? Or in this case, force is applied, so put force here. So we have force like this one. Force we can have a function of t, ft, like this one. So let's rewrite this one. So our equation is cx double dot plus kx equal to t. We can have, in order to solve it, we can take Laplace transform. What you get is csxs plus kxs equal to fs. Yeah. And simply the xs over fs, which is output over input. Force is the input, right? So ft, small ft, will be given by 1 over cs plus k. Yeah. Okay. This is transfer function. Now for different input, we can find out the solution of this one. If you take the inverse Laplace transform, it will give us idea about what is the response to a, so inverse Laplace transform of the transfer function will give you the unit impulse response. So that we have already studied, right? So if you want to find out for this system, if you want to find out what is the response due to the unit impulse, we just find out what is the transfer function, that is xs over fs, and then take the inverse Laplace transform, which will give us the response due to unit impulse, right? Okay, and we take inverse Laplace of this of 1 cs plus k, which is becomes L inverse, and we can write it as 1 over c, 1 over k, can write it as 1 over so yeah, just write 1 over k, and then we have 1 over c times s, c over k s plus 1, yeah, like this one becomes 1 over k Laplace, inverse Laplace of 1 over, let's call c over k as t or tau, let's call it tau s plus 1. Of course, here what we mean tau is equal to c over k. Okay, that's what we done. Yeah. Okay. So this one, inverse transform of this is we can write is equal to, so 1 over k, and then we can have 1 over tau inverse, and then 1 over s plus 1 over tau, like this, rearranging like this one. Now inverse Laplace transform of 1 over s plus a is e to the power minus a times t. So that really means 1 over k tau, and then this is e to the power minus t over tau. Yeah. Now tau we have defined like this one, you know, so tau is equal to c over k, like that, right? So either you can write it as c, or you can write it as, so either you can write it as 1 over c e to the power minus t over tau, or you can write it as 1 over k, like this one, either of the two, right? Where tau is defined like this one. If you plot this one, this looks like something like this. So this is the e to the power, so here the value will be here c, yeah, and from here it will go like this, yeah. So here what this is, right, 1 over c e to the power minus t over tau, okay, where tau is equal to c over k. So this is the response because of the unit impulse. Yeah, unit impulse. Unit impulse, always if you take the inverse Laplace transform of the transfer function we have done earlier, and you get the unit impulse response. And for this, the first order system, for this one, this looks like simply a exponential equation which is decaying basically, right? So which is not increasing but decreasing exponentially, which is given like this. So this example may be asked during your assignment or quiz. Yeah. So in general, if the transfer function is given as 1 over tau s plus 1, then the unit impulse response is given by Cs equal to, or in that case, the Cs, as you know, like in terms of this. So you have the Rs and you have a Ts here, and then you have the Cs here, right? So here the meaning of that Cs, this Cs you're talking about, okay? So then Cs will be equal to the Ts is given by, Ts is given by output over input, just a minute. So since the Cs is given by, the Ts is given by output over input, and if if R represent unit impulse, then Rs simply becomes equal to 1. Yeah. So this becomes unit basically, because the for 1 unit, like if the Laplace transform for unit impulse is equal to 1 unit, okay? Hence it is like this one. So simply Cs becomes equal to Ts in that case, and hence Ct, meaning that C is not in terms of the complex frequency S, but in terms of time, will be simply L inverse Ts. And we know in that case, if in general if Ts equal to 1 over tau s plus 1, where tau is the time constant, you can say. This is in general, because we are not just studying the spring and mass system, but also any other kind of system. So in that case, simply we will get Ct is equal to 1 over tau e to the power minus t over tau, as we got earlier, right? So this is what the finding is basically. Yeah, this is how it will be, and which is unit impulse response we call. Okay. Now this we studied the spring damper system. However, there may be other kind of system. For example, electrical system, something like C. If the inductor is there, and then you have resistance here, R, yeah, like this one, okay, and then you have, this is your output, let us say, this is your input, EI, this is E out. So in this case also, you will see the E out over in E over EI. So if say the equation, let us say, let's formulate in S domain, then what do you get? Okay, so in that case we get this becomes EIS, this becomes EOS, okay, and then you becomes here LS is the Z1, this Z2 is equal to R only, and what do we get? Current IS. So what you get in that case, VEI, so EIS equal to IS, this is let us say called IS, IS multiplied by Z1 plus Z2, and hence EOS is simply equal to Z2IS times Z2 only, hence E naught S transfer function TS equal to E naught S over EIS will be equal to Z2 over Z1 plus Z2, and that is equal to R plus LS plus R. So that's what you get, or simply you divide by that, you get 1 over L over R S plus 1 is equal to 1 over tau S plus 1. So in this case tau, the time constant tau is equal to L over R. So this is another system. Yeah. So since we are studying for all kind of system, this is first order system which is equivalent to, again I am saying equivalent to, meaning that we have the same form of transfer function. So this is equivalent to a spring and damper system simply, right? So like that. Similarly, there may be other system. For example, the you may have op-amp system, for example, right? So in op-amp system, let us say you have something like this, minus, plus, yeah, one resistance here goes one resistance here, equal resistance, and here also if so you could have a 1 R here, and here you can have a, let us say, same kind of system. So resistance here, inductor here, this is the input like this, right? So if this kind of system will also give you the same, because R over this, which is first order, multiplied by R divided by R this one. So this system, this kind of system also, where you have R here, L here, no, and R here and R here. So this system also will be a first order system, and you will have this kind of equation, and hence the solution will be like this. Okay, as I discussed earlier, I would like to revise the terms that I used earlier. So now the closed loop transfer function, which is a standard, you can find it other textbook, in all textbooks it is same, but however the open loop transfer function or open loop gain, those are may differ in different textbooks. Okay, so we are going to follow the Ogata book only, and hence all the terms that is given in Ogata book, we will follow that. So according to that, remember that if we have if this is RS, then we have like this, minus here, plus here, go like this, and here ES term, and let's call it GS, and goes like this. This is CS here, and then like this. Okay, let us say this is called FS, like this. Yeah. So if this kind of block diagram we have, this kind of system feedback loop we have, then these terms we will use. Okay, So this one GS is basically we call CS over ES, which is equal to GS in this case, we will refer to as feed forward transfer function. This is as per your book standard. Okay. Okay. Now CS over RS will be closed loop transfer function. Yeah. And the open loop one is, or FS in this case is feedback, you can say feedback transfer function, and total, like it is something like this. When you have GS here, and then after that, instead of going there, so this is CS here, and then you have FS, and it is, we are talking about at this point. The whole thing we can combine together, we call it GS multiplied by FS, right? And this is known as, so GS times FS is open loop transfer function. Okay. So in book, these are the terms which are used, so we will actually use these terms only. So feed forward, we are talking about this one, this divided by this. Then closed loop transfer function, this divided by this. Then feed forward feedback transfer function, this divided by this. And then open loop transfer function, meaning that we start from here and go here. So this divided by this. Okay. This we can also write it as, so RS open loop transfer function is nothing but RS, right, minus, in this case, minus FS, RS minus FS times CS divided by, so okay, so here we are talking about the okay, so here we are starting from here, we are going here. Okay, so that really means we are this is output, so output is RS, so this is output, so output is CS into FS, sorry, so this will be like CS into FS. Okay, so CS times FS is the output here divided by input. And what is input? Input is here, this one. So input is RS. So RS. Then okay. In this case, basically, we are assuming this this is not there. That's why we call it the open loop. Okay, open loop means these things are not there. So we are talking from here to here only. Okay, so whatever the value, the output is here divided by this one. So if you see here, if we cut the loop, so then this becomes something like this one, meaning that if ES is there, so this becomes ES times GS, okay, and then here, here you get ES times GS times FS, and hence we cannot write like this one, hence we just write like equal to simply ES GS ES GS times FS divided by ES, right? And hence you get equal to GS times Fs. Or simply, when you have the loop like this one, like a adder here, plus minus, you have adder here, what you are going to do is, you remove the adder, yeah, remove the adder, and basically you, this as a becomes input, and here this part as output, and this output over input is the open loop transfer function, which will be equal to this multiplied by this, yeah. Or simply you can write this is equal to the feed forward transfer function multiplied by feedback transfer function. So open loop transfer function equal to the feed forward transfer function multiplied by feedback transfer function. Okay. So this is what is used, and we will use that. Okay. So just to follow the textbook, your textbook, so that we don't have any confusion. Okay. Now if I tell you that if a system, first order system, whose transfer function is 1 over tau s plus 1, if we give a unit step input, okay, then what is the output? So again, this is CS over RS, the way we have been writing. CS is the output and RS reference input, CS over RS, if it is given like this one. The unit step input, so that really means is RS this is RT and this is 0 time, and unit step function means it is 0 0 0, and at t equal to 0 this becomes 1. That's what it is mean. Yeah. So RT equal to 1 for t greater than 0. That's what it means. Yeah. And hence if you take the Laplace transform, yeah, this will be equal to 1 over s. Yeah. So basically this also means ut. This is unit step function RT equal to ut simply. Yeah, simply we write like this also. Yeah. As hence RS equal to 1 over s. So TS, the CS, that is output, is given by RS multiplied by TS, and RS equal to 1 over S and TS equal to 1 over tau S plus 1. And what do we get? From here we get equal to, we can do like this, A over S plus B over tau S plus 1, we can write, which is equal to A tau S plus 1 plus B S plus S tau S plus 1, and from here we will, what do we get? We get a S term, so A equal to, let's write here only, so we get S term which is S, and then we have A times tau plus B, and then we have A term, A divided by S tau S plus 1. Yeah. Okay. that tells us that if you're looking at this one, a has to be equal to 1 and this term has to be 0 because there is no s term up. So a tau plus b equal to 0, where a equal to 1 already. So we get b equal to minus tau, right? And hence cs will be equal to a, which is equal to 1 over s minus tau over tau s plus 1, right? Okay, now ct, now if given input RT equal to like this one, we want to find out what the CT will be. TCT. CT means the CS, the output in time domain now. In the real time, we want to see how it looks like. If the RT is like this one, means when RS equal to 1 over S, which is equivalent to RT like a constant like this one, then how does CT look like? What we know is CS looks like this. So CT will be equal to L inverse CS, and which is equal to 1 over S. That really means UT, or you can say 1 basically. UT minus then you have a tau, and this you know already becomes 1 over tau into 2 minus t over tau. So that you know. So simply you get or you can write 1 minus e to power minus t over tau, and where for t equal to 0. Okay. So the response, if you plot this one, how it looks like? This will look like this t, this is ct, this we are plotting, this ct, and t equal to 0, you have 0, and then at t equal to infinity, the whole thing becomes 0, and hence you have 1. So this will look like something like this. So it will go like this. At 1 it becomes constant. So this is 1. So this is what this looks like. Another way of looking at this system is also in terms of, say, you have a, so far we assume this to be a open loop system. Okay, when you say open loop system means what? So you have open loop system. That really means that you have one input Rs, and then you have a transfer function Ts like this, and then you have Cs output. That is, there is no feedback. No feedback means this is open loop system. For this, we are assuming Ts itself is given like this one. For example, one example could be the spring and damper system itself. Okay, so like this, Ft. This is one example. However, this one can also be a feedback or the closed loop system. So closed loop system. The closed loop system, in that case, will be something like this. So we have Rs here, and then we have Gs something, then we have Cs here, then going backward. So maybe the gain is, the feedback gain is 1 only, so it is like this one, and hence you have like this here, like this, and like this. So this is plus, here minus, like this. Okay, now here it could be 1 over tau s. Why? So if feed forward transfer function, this is Gs, right? So we call it Gs, is 1 over tau s. So This example will come, for example, if you have a flywheel, for example, right? So flywheel, so tau, different tau here. Let's call it, this is torque one, so T1, this is torque, right? This tau, this is time constant, there is difference, yeah? This is time constant. So tau equal to J, then omega dot, right? So we get tau, the tau 1s, tau 1s equal to Js, sorry, J times S, then omega s, let us say, yeah? And hence output over transfer function, in this case, this Gs, or let's write just Gs because we're talking about just this system, yeah? So only this system could be something like this. So Gs will be equal to the omega s divided by tau 1s equal to 1 over Js. Right? So here J will be something like a time constant. Yeah, so just giving one system, it is like this one. And now let's make a feedback loop, meaning that I'm measuring the output, means this omega is angular velocity. We are measuring the velocity and giving the feedback to this adding junction, and then we are comparing. So the closed loop, for this one, the closed loop transfer function Ts will be equal to, as we know, 1 over tau s divided by 1 plus 1 is the gain, 1 over tau s. We write like that, and hence equal to, we get 1 over tau s plus 1. See? Same thing, this one, we can also have exactly the same transfer function as this. System is different. In this is a open loop system, but system itself has this kind of form, transfer function. Although this is the open loop system, there is nothing going back. Here this is closed loop system. Hence the feed forward transfer function is 1 over tau s, but overall the closed loop transfer function comes to 1 over tau s plus 1. So we can have both kind of system. Yeah. So that means this flywheel system can be made similar to this system. However, we need a feedback loop to make it system something like this. Now consider this one. In real time, this will be RT, right? See, this is in complex S domain. Now inverse transform of inverse Laplace transform of all these. If you study, this becomes RT, this becomes CT, and let us say you had a unit step function here. So RT is unit step function like this. Yeah, T like this one. This is the one equal to UT, and you know CT in that case. In this case, since the transfer function, overall transfer function, meaning the closed loop transfer function is this, and for that we have already solved how the CT will look like, and this will look like something like this. And what is the value? CT will be 1 minus E minus T over tau. Okay. So this what we call it ES, right? So ES equal to RS minus CS in this case. So ET you can write which is also known as error. Et equal to RT minus this. So RT minus CT, right? So RT is 1, right? UT, RT equal to UT basically, this is also U2. So equal to 1 basically, T more than 0. So equal to 1 minus Ct is 1 plus e to power minus t over tau is equal to e to power minus t over tau. Right? Okay. Now, this is error. If we want to find out a steady state error, then Et as t tends to infinity. Steady state error equal to E at time equal to infinity is equal to t tends to infinity. This becomes 0, hence 0. So in this case, what we see is a steady state error is 0 because this is RT. So basically, this is what the RT is. This is RT is, or small RT, and this is CT is, and in long time RT becomes equal to CT, right? So the first order system has a steady state error equal to 0. So this is the advantage of first order system, but not every system is first order, of course. Okay, so this may be asked in a quiz and all, steady state error for first order system and all, and this same system being as closed loop system and open loop system, okay, but the same overall transfer function. Yeah, so this closed loop system is equivalent to a open loop system which this transfer function 1 over Ts, you have 1 over tau s plus 1, like this one. This is Rs and this is Cs. Open loop system, closed loop system, in this case open loop system. So basically the transfer function of this overall transfer function and overall transfer function both are same in both the cases. Now unit response is very important for a first order system, as we have seen that if RT is UT, meaning that the unit step function, yeah. So, and this is input, and Ct is 1 minus e to the power minus t over tau, right? That's what it is. And so that means this is what 1 is, and this goes something like this. Yeah. So this is t. So first is from here, this will be tau, t equal to tau, and here the value will be in this case put t equal to tau. So Ct is equal to 1 minus e minus tau over tau equal to e minus e to power minus 1, and which will be equal to 1 minus 1 over e, basically is equal to 0.632. So this will be 0.632 or 63.2% of the final value. Yeah. Okay. And similarly, you can find out for this is t, then this is equal to 2 tau, then 3 tau, and so on. Accordingly, you can find out the value. So for tau will be like this one. 2 tau will be equal to 1 minus e minus 2 or 1 minus square, there will be some value here. At 3 tau, this will be 1 minus e to minus 3 equal to 1 minus 1 over e3. So these will have some values. So this value will be around 0.865. This will be 0.95. Yeah. So here this value 0.865 and 0.95. So here and this is 1. Yeah. So this is how it looks like. So these are the characteristics we say basically. Yeah. So you can say that this tau is the time when the output is 63.2% of the final value. So you can also define the time constant like this one. But this is how the output looks like. This is the output means response to the unit step function. Yeah. So this is Ct is equal to 1 minus e minus t over tau, which is the first order response. So why is it important to know how it behaves, right? So this is 95% of the desired value. Let us say at this, if you want to study 4 tau, so here it will be somewhere here, yeah. Let us say it goes like this. At this point, so at 4 tau also we can write equal to 1 minus e to power minus 4 equal to 1 minus e to power 4, which is equal to 0.982. Okay, it's important because of the response time, very important. So something called response time. Response time, meaning that is as in control system, right? A reference, you change the reference, and maybe you change the reference like a step input. You've given the step input, you have increased or decreased. You want system to respond fast enough, you know. So this tells you the response time. Response time is basically time required, you can say time required to achieve the desired value within within 2% of the desired value. So this is my language basically. It's a technical simple language. What is meaning is that in this case, let us say you are starting from 0 and you are increasing to 1. Now you have changed the reference you have changed. This is your reference RT is equal to 1, right? And this is the output which goes like this one. So at 4 tau, if you see, it took 4 tau to reach within 2%, because within 2% means 98% or 0.98. So at this 4 tau, you will see the value is 0.982, so which is within 2%. So the response time in this case will be equal to close to 4 tau in this case. Right? So this response time is important. Like this is something that tells you how fast a system is, how closely it follows the reference or input. So you also want the system to be fast, not that like you are giving input and then it is taking very long, right? Especially when tau is very big. Let us say if your tau, the time constant is very big, then what happens? You have given this input reference and then it is taking something like this, going, so taking forever to reach, right? This kind of thing you can see, for example, in heating system, right? So when you switch it on, right? So, and you set from the room whatever temperature is, say 15 degrees Celsius, and you set it to 25 degree. But the heater will start, but not immediately the temperature will rise, right? So it will be very slow, and then it will be where close to the desired value, right? Close to 25 degrees Celsius that you have set. So that really means the response time is very large in that case. So this is just to compare the system basically. The response time is important parameter. For the same first order system, the transfer function of which is given by 1 over tau s plus 1. If somebody tells you which is equal to Cs equal divided by Rs, if somebody says that RT, which is the input, right? This is the input. If this is equal to T, for example, yeah? So this is a ramp equal to T. It go like this. So T here and this RT here, like this. Okay, so this is the ramp input. Then what will be the output, right? So in that case, what will you do? You will take a Laplace transform first. Laplace transform RT, which is equal to Laplace transform over T, which is equal to 1 over S square, right? And which is equal to Rs basically, right? So Cs will be equal to Ts multiplied by Cs, and Ts is 1 over tau s plus 1, and Cs multiplied by, sorry, Cs, this is Rs, Rs equal to 1 over S square, right? Which will be equal to, so you have S, so that will be, let us say As plus B S square plus C over tau s plus 1, something like this, yeah, okay. Yeah, and what do we get? We get equal to As plus B times tau s plus 1 plus Cs square divided by S square times tau s plus 1, which is equal to, so S square terms we can have, so A tau s square plus C, that is S square, plus just S term, so we have B tau plus A S term, and then we have constant terms, that is B divided by S square tau s plus 1, and this gives us clue. The values will be B equal to 1. This tells us B has to be equal to 1, comparing the coefficients here. Then since B equal to 1, A equal to minus tau, so since this equal to 0, right? B tau plus A equal to 0 because there is no S term here. So, and B equal to 1, so A equal to minus tau, so this is done. And here we get C equal to A equal to minus T, so minus tau square plus C equal to 0, hence C equal to minus tau square. So basically what we get from here is this value, so we get A which is equal to minus tau, so minus tau s plus 1 over S square plus C is minus tau square, so minus tau square over tau s plus 1. So that's what we get, yeah, is equal to, we can have 1 over S square minus tau over S minus tau square tau s plus 1. So that's what we get. Okay, now CT equal to inverse Laplace transform Cs, which is equal to 1 over s square, so comes back to t term. Then we have minus tau over s. 1 over s is one term, so minus tau, basically 1 over s is nothing but unit, right? So unit, we can, the unit step function we can replace with 1, because all these values are for t more than equal to 0. So t minus tau we get from here, minus, and from here we get tau square, and then we have 1 over this value, 1 over tau s, nothing but 1 over tau e to power minus t over tau, right? Okay, and this is what we get. We get equal to t minus tau minus tau e to the power minus t over tau. Okay, there is something wrong here, so let us see here. So this is b. Okay, so b is equal to 1, and hence you have 1 here. It is fine. Second thing is 1 here, so a becomes minus tau, so minus tau s plus 1, so is fine. Now a equal to minus tau, right? The minus tau, so put minus tau here, so becomes minus tau square plus c equal to 0, hence c equal to tau square. So c equal to not minus tau square but tau square, right? So c equal to tau square, so hence we should have plus here, yeah. So plus here, hence we will have this, hence we will have plus here, yeah. Okay, so the value will be my t minus tau, and then you have 1 minus e to the power minus t time. So this is Ct. Okay. Now let us say for the closed loop system, when you have 1 over tau s here, and here you have Cs, here you have Rs, and here you have plus here, minus here, goes like this, system like this one. For this system, the closed loop transfer function is nothing but this only. And if input is ramp like this one, Rt equal to t, then Ct is like this one. So E, this is Es, right? So Es, so Et, Laplace transform, inverse Laplace transform of Es basically will be nothing but, in this case, inverse Laplace transform of Rs minus Cs, which is equal to Rs, nothing but Rt minus Ct. So here this is Rs minus this, right? So Rt minus Ct, and Rt is nothing but t. Rt equal to t you have given in this case, minus Ct. Ct is this. So t minus t minus tau, 1 minus e to the power minus t over tau, right? Or t cancels out, minus becomes plus, equal to tau e to the power tau times 1 minus e to the power minus t over tau, like this. So this tells you the error here, yeah, error as a function of time. So error, the steady state error, when you say steady state error, the steady state error E t tends to infinity is equal to E t tends to infinity, t tends to infinity, this becomes 0, this part, so equal to tau. So what you have is a steady state error in this case, this system will be tau. Yeah. So this is the first order system, but the input is ramp basically. Yeah. So if the input is ramp, then a steady state error becomes tau in that case. Earlier we found that for this system, when the input is a unit step function, then steady state error is 0. Okay, but if your input is a ramp, then there is a steady state error. So that really means it will be something like, if you plot this one, this is the input, what you want, right? So this is a t, goes like this one. Yeah, this time here you are plotting both RT and CT both, and your value at error is at t equal to 0, 1 minus 1 equal to 0. So at t equal to 0, error is 0. So both are the same place, and then after that it becomes something like this. Okay, so what you see is after infinite time, means after long time, you will see there is a difference between the two. At the same time, there is a gap equal to tau, like this. Yeah, this is what it means. So this is the error, right? So this is what the meaning of E is. So response of this first order system and the steady state error for the ramp input may be asked in your quiz, yeah, or in the continuous evaluation path. Yeah, so you know how to find out a steady state error, right? So that is all for today's. So we understood what the first order system is, how the response of a first order system looks like, response because of a unit impulse, a response due to a step input, unit step input, and also the ramp as well. Yeah, we understood the steady state error as well. Okay, so tomorrow we will learn about the second order system. Second order system you know already. So underdamped, critically damped, damped condition, all those things. You know, so it will be easy for you. I would suggest that you revise those second order system, the underdamped, the critically damped system. You know, so it will be easier to understand. So in any case, I will go very fast in that. Because you have done already. Okay, see you tomorrow.